Okay, we're going to do some of my old Apex notes for this assignment because I can't find a very good virtual assignment for you guys. So what we're going to be learning about today is that the Earth contains an ever-shifting magnetic field that protects us from getting bombarded with too many charged particles. So some main points is that they all have a north pole and a south pole, and opposites attract. So the same poles will repel. So what you have here is the magnetic north, which kind of can move around, and then there's geographic north, which is where Santa lives. Throughout your notes, you'll see that what you need to write is in the dark gray boxes. All right, so there are two types of poles. The geographic poles are the poles based on the Earth's rotation, and so we think the Earth spins like this, but in reality its axis goes like this. So this would be the North Pole. And then there's the magnetic poles. These are two opposite ends of a magnet, and that's how the Earth is. All right, so there are types of magnets, permanent magnets and electromagnets, and the material that is always magnetized is a permanent magnet. So an example would be the door of a refrigerator or something like that. Electromagnets is something that is magnetized due to electricity, like a big crane at a car park, or a CAT scan machine. I couldn't think of the word. Please pause the video as you need to in order to take these notes. All right, magnetic field lines. These allow you to figure out which way a magnet will align with the lines exiting the South Pole and entering the North Pole. So the magnetic field surrounding the Earth is called the magnetosphere, and the magnetosphere deflects harmful radiation from striking Earth, and it creates these beautiful auroras near the poles, also called aurora borealis or the northern lights. So because we have this magnetic field protecting us from things from space, including some harmful radiation, it reacts with the ions in the air to make these beautiful colors. This is another reason, though, that we have a magnet that will align, so like with a compass. So the lines exiting the South Pole and entering the North Pole all have to do with the magnetosphere. All right, so the magnetic North Pole, this is not the geographic North Pole, which stays in the same place. The magnetic North Pole shifts about 10 kilometers a year. So last year, we used my compass during forensics quite a bit on my phone, and I noticed this year that the North Pole is actually facing just a little bit differently than it did last year. And so that has to do with our compasses moving because of that. Declination is the angle difference between the geographic and magnetic North Poles. So there's actually a website where you can estimate that, and you could go there, put in your zip code, and compute the declination. This is not something we need to memorize. It's just a fact that was a part of our lesson. Moving on, so pause if you need to. So the north and south poles of Earth's magnetic field cyclically switch places. So this is an important fact. Pole reversals. The poles reverse every long time. I know that 250,000, 740,000 seems like a big difference. But what we need to see here is that it's really not that big. It's like saying, like, typically, every 7 years we get a particular snowstorm, but this year, this time it happened in 14 years. Like, it's really not that big of a difference in the grand scheme of things. So the poles reverse, meaning that the South Pole becomes the North Pole and it moves up. It doesn't move. I mean, they don't, but it does change the magneticness of them. So they basically switch. So what does this mean? How do we know this? So some evidence for this we've been learning convection currents and how warm things rise and then cold things sink. And so knowing that warm things rise and cold things sink, and knowing that in this picture here, right there, that is the ocean floor. And at some point, we have to have this magma that comes up and it's creating the bottom of our seafloor. So when it pushes up, it creates this new part in the middle right here of the seafloor. And as it moves out this way, new material is pushed up here. And so when things are pushed up and it gets pushed out in this direction, now the very bottom of the seafloor, different things like magnetic magnetic fossils or rocks get stuck in the ever moving, changing ocean floor. And I mean, it moves very slowly. We couldn't see it. And so they get stuck there and then they fossilize. And there are areas where the crust here is actively being formed, such as the mid-oceanic ridges. And this is important because as those things get stuck there, they're going to point towards the magnetic north in this case. But when the poles reverse, they start pointing in the opposite direction. Not the stuff that's already fossilized, but the new things before they fossilize. Let's get into that a little more. All right, so let's talk about the convection first. Hot lava rises through the seafloor, cools, and solidifies, showing the alignment of magnetic minerals within the seafloor. A banding pattern on the seafloor is evidence of rock age. Young rocks are near oceanic ridges. Older rocks are further away. Banding patterns also show pole reversals that have occurred throughout Earth's history. One of the assignments we're going to have soon that you won't be able to do in class, but you will be watching, has to do with showing how this works specifically. So what you need to know for now is that the seafloor is spreading because it goes up where that magma is, and then it stretches outward. And so anywhere where that comes up is going to be the newest, and the further you get from that point, the older it is. Kind of like the hair on our heads. The hair close to your scalp is newer. The cells down at this end, they start to break, and the end of my hair is much older than the roots of my hair. So as my hair grows out, I can actually see time, as it were, because I had my hair done back in January, and it's already grown out this much. I can see the color difference in my hair as it grows. And the same goes for the ocean floor. It's kind of like it's growing hair, but it's horizontal instead of vertical. So pause the screen and continue writing as you need, but I am going to continue on. The knowledge of the structure of Earth's interior has allowed scientists to devise a theory as to why the Earth has a magnetic field. It is called the dynamo theory. So we're talking about more evidence of the inside of the Earth. So we have the liquid outer layer that we know is made of iron, and that has to do with part of the magnetosphere and all of that. And it's constantly moving in convection cycles here in the outer core because it is liquid. So inner core is red, outer core is in yellow. So what we see here is that the stuff that is getting near the inner core is heating up quite a bit, and hot liquid is going to rise back to the surface. And as it gets closer, this not being the surface of the Earth yet, as it gets closer to the mantle, it somewhat cools, causing it to fall again back towards the inner core. And it continues to move in this fashion, and that is convection. So the inner core is a solid spinning sphere. I like to think of it, if you've ever been to the Louisville Zoo, they have this big globe when you first walk in, and it's sitting on a water fountain right here, and the water is causing it to move all around. And that's what I like to think of as the inner core. It's spinning around due to this constant convection all around it. The inner core is made of iron and nickel, which is a similar composition to the outer core. All right, so the dynamo theory is that the liquid outer core swirls around the inner core because of convection, allowing the iron in the outer core to act as a conductor and create a magnetic field. What I'm going to have posted as well is a video about densities and convection, and I expect you to listen to that as well. This is where you will be really taking a hold of your own learning, because if you don't watch those videos, your quizzes and tests are going to be much more difficult for you when we get to them. So hold yourself accountable and please complete all the videos. All right, moving on. Those are the end of the notes. I'm not going to have this quiz to take. Where I'll just go over it with you. These are quiz questions that you're going to see in the future, so you might as well get the answers now. Where does the convection happen that causes Earth's magnetic field? Convection is occurring in the outer core, and it's causing the ever-spinning inner core. The magnetic field will move magnets and moving charged particles, only moving charged particles, and only uncharged particles. And it would, of course, move magnets and charged particles. Which usually contains a permanent magnet? Earth, a powerful crane, a compass, an MRI machine. We know that it's not an MRI machine or a powerful crane. And in fact, Earth is not a permanent magnet either. The sun is pretty permanent, but in general, a compass is a permanent magnet. Which of the following is the magnetosphere not responsible for? Earth's gravity, the aurora borealis, blocking cosmic rays, and Earth's magnetic poles. And what we've learned here today is that Earth's gravity is not responsible for the magnetosphere. Striping on the seafloor around ridges occurs because the seafloor is getting thicker, the seafloor is spreading, the seafloor is slowly melting, or the seafloor is shrinking. In fact, we know it's not shrinking or melting because it is getting bigger. And so the seafloor is spreading due to being pushed up by convection.